Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW Gulf. So, students, I welcome you all to your Achievers Ultimate Recap. That means we are going to revise the complete chapter of our Achievers batch. So, students, till now we have done a lot of chapters, we have done a lot of sessions in which we have revised our previous chapters. But now, today, it's turn of the chapter States of Matter. I hope so, students, you have revised the previous classes, you have gone through the topic very thoroughly. But today, what we are going to do? We are going to do a quick recap. Now, in this particular recap session, we are going to discuss each and every topic in detail. But yes, you have to open your notes, you have to open your NCERT so that you can understand this and you can create your short notes. Now, this kind of notes, like the short notes part, will be helpful to you in your examination as well. For example, if your exams are approaching and you have a lot of work to do, so what you can do is you can revise your chapter with your quick notes. So, this is going to help you in that as well. Now, students, let us start this class with a beautiful smile. Right, as I've already told you, what are we going to do? We are going to start with our chapter, that is states of matter. And in this chapter, we are going to start with the initial topic, that what exactly we refer to as the states of matter, such as solid, liquid and gaseous. And you very well know that the gaseous state of matter we are going to cover in this particular part. See, we do have liquid state, we do have solid state. Solid state will be seen in your Triumph batch, that is in your class 12 standard. Okay, we understand solid state chapter in depth in class 12th, while in class 11th we have a chapter gaseous states. But yes, first of all, I'll let you know how do we divide them into solid, liquid and gaseous based upon the forces or the theories that work upon, right? But yes, after that, as I was saying, that we have three states in detail. First of all is the gaseous one, we'll be covering in 11th, the solid in the 12th and the liquid in the physics part, right? So let's start this class. Yes, everyone. So how are we going to proceed? What are the topics we are going to do in this particular class, or what is the sequence? I would say you all should know that. So the very first thing that we are going to start in today's class is going to be what? The very first is the general introduction. Now, in this introduction part, students, I will let you know that what exactly are the states of matter. That means in depth, why do we classify into solid, into liquid, into gaseous, right? Why do we classify them? Okay, accordingly. So then we are going to understand about, the very basic things over here, such as what are the nature of gases, okay, what are real gases, what is an ideal gas. So we are going to understand about gases in detail. After that, students, we shall be understanding about, all the gaseous laws that works upon. For example, the Boyle's law, the Charles law, the Gay-Lussac's law, Avogadro's law, okay, and then the ideal gas equation. So we are going to do that as well. That means we are going to do the laws part. After law, students, we shall be understanding about ideal gas in detail, ideal gas equation in detail, and then we shall be proceeding towards the Graham's law of diffusion. The Graham's law of diffusion. After that, students, we shall be focusing upon your KTG, that is kinetic theory of gases. Kinetic theory of gases. And at last, we shall be understanding about the correction terms. For example, the correction in volume, the correction in pressure. So we'll be understanding about that as well, right? So here we'll be seeing correction in volume and correction in pressure. That means we are going to see the real gas equation over here. The real gas equation over here. So this is going to be the complete recap part that we are going to do according to the sequence. So first of all, I'm going to start with the very first topic of yours, that is going to be what? That is going to be exactly the states of matter, right? If I let you know that in order to understand states of matter, we'll be observing, students, that two forces are there. Two forces are responsible for them to classify them into solid, liquid and gaseous, right? So what are that two forces? What are that two forces that I'm talking over here? So the very first force that I'm talking about over here is a force of attraction. What is that, ma'am? That is force of attraction. Force of attraction. And the second one that I'm talking about is the tendency to escape each other. Tendency to escape each other. Now, the tendency to escape each other, in other words, can be referred to as the repulsion forces. Which kind of forces, students? The repulsive forces. The repulsive forces. Let's understand about them with the help of a general diagram. See, students, as I've already told you, this is a kind of a recap session. So, in a quick few minutes only, you'll get to know that how we have classified them as per these forces, right? So, if I'll talk about the very first part over here, if I'm referring to your term solids, what I'm referring to your term solids, what happen in solids? If I'll talk about these two forces in the case of solids, we observe that in solids there is a greater force of attraction. But yes, if I'll talk about the force of repulsion, it is very, very less. Almost, I would say, it is almost negligible if you observe the particles arrangement. So the particles in solids are so closely and tightly packed to each other in such a way. If you'll observe it over here, it shall look like this, that the particles are so tightly attached with each other so that they don't even have, this much space so that they can move from one position to the another one. So they don't have that part, right? That means if I'll talk about the forces over here, it has a strong force of attraction while it has a very, very, very weak force of repulsion over here. Okay, if I'll talk about the case of liquid, students, if I'll talk about the case of liquids. So what happens in the case of liquids? Yes, particles do have both the forces of attraction as well as the forces of repulsion. How, ma'am? See, over here, if I'll talk about the force of attraction, it is less than the solids. But if I'll talk about the force of, I was about to say force of attraction, right? So if I'll talk about the force of attraction, they have less than the solids. And if I'll talk about the force of repulsion, they have less than the liquids, right? So that means particles are present but not that much close as we have observed in solids. So here we can clearly observe that there is a difference of space between the two particles, right? They exhibit some kind of space. This shows us that yes, ma'am, there is a force of repulsion also, right? But they are not much as attracted as solid. Why? Because there is a gap over here that you can clearly observe. Now, let's talk about the third part, that is the gaseous one. So, now in the case of gaseous, what do we see? We see that the force of repulsion, is the dominant over here. It is in a much greater extent if I'll do the comparison with the force of attraction. We'll be observing that the particles are present at so much far distance from each other. They are present at a far distance from each other. That means there is a larger force of repulsion and a very, very less force of attraction if I'll talk about the case of gaseous one. So this was all about, if I'm talking about the forces that exhibit between the particles and how do they arrange themselves in the case of solid, liquid and gaseous one. So now we are going to majorly focus upon the topic that is about the gaseous ones, right? So starting with the gaseous ones, students, there are few terms or I would say such as the measurable properties, I would say, are pressure, volume and temperature. So let's understand about them in detail, right? Because there are 4 parameters that we need to do. So first of all, let's start with the measurable properties, everybody. Measurable properties in the case of any of the particles, if I'll talk about, will be temperature, will be pressure, will be volume, will be number of moles, or I would say the amount of gas. So there are 4 factors that I'm going to talk again and again. That's pressure, volume, number of moles and temperature. Okay. The whole scenario revolves around it. That means if you're going to start with the laws part also, you'll be observing that all the laws are based upon all of these 4 parameters over here. So first of all, the measurable properties, that means something we can measure easily, right? We shall start with temperature. Now you very well know that we can, calculate temperature with the help of 3 scales, that is Kelvin, Celsius and Fahrenheit, right? And we can convert one into the another with the help of certain formulas that we do have with us, right? But in general, if I'm talking about any of the formulas that you shall be observing in the gaseous laws chapter or in the gas chapter, you have to take temperature in Kelvin. Always remember that, students. In numerical, what happens is students knows everything. When they are going to solve the question, they just take temperature in Celsius and the whole question is wrong. So do remember this part. Let's understand about this and their conversion. How do we need to convert them into Kelvin, right? So basically, see, temperature, if I'll talk about, we should know know that if we have to convert a temperature of Celsius into Kelvin, then into Celsius we need to add 273. So if we're adding 273, for example, if I have 25 degrees Celsius and I say that please convert into Fahrenheit. So what are you going to do? You'll add 25 with 273. What are you going to get? You will get 298 Kelvin, right? And if you have to convert your Kelvin into Celsius, that means you have to subtract 273 from it. And if you have to calculate the approx value, students, you can go with 273.15. But yes, in journal, we generally add 273 directly, right? So basically, this is the conversion that you should always know about it. Moving on to the next one, we have pressure of a gas. Now, what is the pressure? Pressure is something that force exerted per unit area. Yes, we have been listening to this term from your lower classes, right? From the 9th, from the 10th. And we very well know what is pressure. Pressure is force upon area. Very simple. So, according to the laws of motion, pressure is defined as force applied per unit area, right? So, this is force by area and the unit is Newton per meter square, or even I can say Pascal. Clear everyone? So this was all about pressure. Yes, in on question paper, you shall be observing pressure in terms of ATM, that is atmospheric pressure. In terms of, you will be observing in mm of Hg, right? So these are the units that you shall be observing in the questions. Let's see the next part. Now we have atmospheric pressure that I was saying 1 atm. What is atm? Atmospheric pressure. Let's understand about that as well in detail. Yes. Okay. So if I'll talk about the atmospheric pressure, see students, the actual value of atmospheric pressure depends upon temperature, location and the weather conditions. The pressure due which is exerted from the upper part, if I'll draw a diagram over here, one is the pressure that is exerted by the gas particles on the walls of container, and another pressure is the atmospheric pressure, or I would say the external pressure that depends upon various factors such as the location, such as the weather conditions. The atmospheric pressure is measured using an instrument called barometer. Okay students, and this is barometer measuring atmospheric pressure. Okay everybody? Okay, now students, let's focus upon the laws that I was talking about. So if I'll talk about the laws with regard to this chapter, the very first law that we need to study is going to be your Boyle's law. Which kind of law, ma'am? The Boyle's law. Okay, and if I'll talk about the Boyle's law, students, in Boyle's law, see, we have to consider these 4 parameters: pressure, volume, number of moles and temperature. Okay, now what is going to happen in all of these 4 laws over here? You have to keep any of the 2 constant and you have to establish a relationship between the other 2 that are left over. So over here in the case of Boyle's law, remember that students, you are going to establish a relationship between pressure and volume. And what is going to be kept constant over here, ma'am? Number of moles or amount of gas and temperature, right? So we can say that for a given amount of gas, when temperature is constant, pressure is inversely proportional to volume of a gas. So this is stated by the Boyle's law that for a given amount of gas, now what is a given amount of gas? The number of moles, the N value. Okay, when temperature is constant, now you have kept N and T both constant and you have established a relationship between pressure and volume. And what is told over here, that pressure is inversely proportional to what, ma'am? Pressure is inversely proportional to volume. Moreover students, if you will see this part over here, when we'll get rid of this directly proportional sign, what are we going to introduce? We are going to introduce a constant K over here. So pressure is equivalent to K into 1 by V. Now can I take this V over here? What I'm going to get? PV is equivalent to constant K. PV is equivalent to constant K. So now for 2 different situations, can I write it as P1 V1 is equivalent to K? Let us say this is your first equation. Similarly, can I write it as P2 V2 is equals to K? Because see, the multiplication of pressure and volume, that is equivalent to the constant K, right? Right? So if I am equating both 1 and 2 all together, what I'm going to get? P1 V1 is equivalent to P2 V2. So this is my one formula, this is my first formula, this is my second formula with regard to Boyle's law. With regard to what, ma'am? With regard to Boyle's law. Let's talk about the graphical part with regard to this part now, the Boyle's one. So if I'll talk about the graphical section, if I'm saying that let's plot a graph between pressure and between 1 by V. So what are you going to get over here? See, it's very simple. You basically know that pressure is equivalent to K into 1 by V. Now only we have seen. So can I write it as Y is equals to mx plus C? Can I go with this part? Right. What is the y? Y is P. What is x? X is 1 by V. What is m? Just see. What is m? M is K. And what is C? C is 0. Now, if C is 0, students, you should know. If C is 0, that means intercept is 0. What is C? If you don't know, C is basically the intercept. C is basically the intercept. And if intercept is 0, that means it is cutting the y-axis on a particular point. What is that? That is 0. That means it is going to start from here. Now, what is the value of m? A positive K. So, this is going to be your m. This is going to be your m. That is K. This is slope. This is what is slope. Because if you are increasing, because see here, pressure is directly proportional to 1 by V. So, we are getting the straight line graph. But, important part. See, if I'll draw a graph between pressure and volume, what are you going to get? It's very simple, ma'am. Pressure basically is inversely proportional to volume. If you are increasing pressure, volume will decrease. If you are decreasing pressure, volume will increase. So what kind of a graph you're going to observe over here? This hyperbola. This hyperbola curve you're going to observe over here when pressure is inversely proportional to volume. Okay, now there is one more key concept. Many questions are asked from this part as well. If I'll keep pressure over here and 1 by V over here, and I'll observe that these are various slopes. This is T1, this is T2, this is T3. Now, just write me the increasing order of the temperature over here. So, how are you going to calculate? How are you going to calculate? Let's understand this. See, students, now I have told you that pressure into volume is equivalent to constant K. You very well know this part now. We know that PV is equivalent to nRT. And PV is equals to K. So, K is equals to nRT. Very simple. That means K is directly proportional to temperature. What is K? What is K? K is basically your slope. Now only we have seen the graph. That means more the slope, or more the slope, the temperature which has, if I'll say the slope which has the highest will have the highest temperature, no? So if I'll draw that again over here we have pressure, here we have 1 by V, and here we have 3 temperature curves. This is T1, this is T2, this is T3. Here T1 is a greater slope, right? That means if it has a greater slope, it has the highest temperature. Why? Because more the slope, more will be the temperature. So what is going to be the order? T1 is the highest, then is T2, and then is T3. So such even questions are asked in the examination, everybody. In the examination. I guess you very well know this now. Okay, now let's start with the next law of ours. Yeah, okay. So now comes the second one, that is going to be which law, ma'am? Charles law, ma'am. Okay. Okay, if I'll ask about the Charles law, what happens in the case of Charles law? Here, two of the things are kept constant, that is pressure as well as the amount of gas. What is kept constant, ma'am? At constant pressure for a given amount of gas, for a given amount of gas, volume is directly proportional to temperature. That means what do you observe here? N and P is basically kept constant, and we see a relationship between volume and temperature. See, in the previous case, pressure was inversely proportional to volume, but over here, volume is directly proportional to temperature. That means if I'll get rid of this directly proportional sign, can I introduce this K constant? Volume is equals to KT, right? So, can I write it as K is equals to V by T? Now, for two different states, let us consider K is equals to what? V1 by T1. Similarly, can I say that K is equals to what? V2 by T2, everyone. Let's say this is your equation number first. Let's say this is your equation number second. If I am comparing both of the equations all together, the first and the second, what I am getting? V1 by T1 is equivalent to what? V2 by T2. So, this is my new formula for this particular part. For Charles law. Yes, everyone, is it clear to each and everybody of you? That's really great. Now, let's draw the graph with regard to volume and temperature. See, if I am drawing a graph with regard to volume and temperature, I know volume is directly proportional to temperature. If you are increasing temperature, volume will increase. direct straight line. And if you want to confirm over here, see, you very well know V is equals to KT. Y is equals to again mx plus c. See, here is 0. What is m? M is slope, m is k, positive k. So we'll get this curve. Now see, this is basically in what? In Kelvin. Now you have to do in Celsius as well. You have to do the temperature graph in different Celsius and the Kelvin. So you will be observing different kinds of graphs. See, if it is in Kelvin, then you need to subtract 273. So basically this graph is going to be like this. This temperature is minus 273 degree Celsius. This is when temperature is taken in Celsius. And this is when temperature is taken in Kelvin. Okay, and this temperature is referred to as your absolute temperature. Clear? This was starting from 0, and you have to take in basically, so you have to convert it basically. What I'm doing is we are converting them all together. When you have to convert Celsius into Kelvin, you are adding 273. When you have to convert Kelvin into Celsius, you are subtracting 273. So when we'll subtract, it will be minus 273 from 0. No? So these are the two different graphs that we obtain over here. Is it clear to each and every one of you? That's really great, students. And similarly, one such questions from this part is also asked. If I'll give you a graph between volume and temperature, we very well know that they are directly proportional. So can I say this is your P1, this is your P2, and this is your P3? If I'll ask you, students, which pressure is more? Again, you have to do in the same way as you did for the previous one. So what you need to do over here, you are saying that, ma'am, volume by temperature is equivalent to K. Very simple part. Ma'am, we know that PV is equals to nRT, right? PV by T is equals to nR. Can I say that P by T is equals to nR by P? If I'll take the pressure over there and temperature over here, we get this term. V by T is K. So can I say that K is equals to nR by P? So what can I observe over here? That K basically, ma'am, is inversely proportional to pressure. K basically, ma'am, is inversely proportional to pressure. That means more the slope, least the pressure. More the slope, least the pressure. So the highest pressure will be of P3, there is P2, and then is P1. I guess this is now clear to each and every one of you. It is quite different from the previous one. In the previous, as we generally know that K was directly proportional to what? Temperature. But over here, K is inversely proportional to what? Volume. Clear, everyone? Okay. Let's discuss about the next law now. The third law. Third law basically states about Gay-Lussac's law. Now, in Gay-Lussac's law, what happened here? What are we keeping constant? We even need to see this. Here, volume is kept constant and number of moles is kept constant, or same, I would say. So we can say that for a given amount of gas at constant volume, pressure is directly proportional to temperature. Pressure is directly proportional to temperature, right, everyone? So we can say that pressure is directly proportional to temperature for a given amount of gas. So when we have to get rid of this directly proportional sign, we can introduce a constant K. P is equals to K into T, right? What will be K? K will be P by T. Now for two different states, what we can write over here? For two different situations, K is equivalent to P1 by T1. Similarly, K is equivalent to P2 by T2. If I have to compare both of them together, what I'm going to get? I will get P1 by T1 is equivalent to P2 by T2. So this is my new formula for which case? For the Gay-Lussac's law. Clear, everyone? Clear, everyone? So if I have to draw a graph between pressure and temperature, it is going to be a straight line again because they are directly proportional to each other. Now, students, comes your fourth, that is going to be your Avogadro's law. That is going to be your Avogadro's law. So if I'll talk about the Avogadro's law, students, what you need to take care of here over is that it states that volume is directly proportional to the amount of gas. Volume is directly proportional to the number of moles, or I would say the amount of gas. That means it is not inversely, sorry, it is directly proportional to number of moles, or I would say directly proportional to number of molecules. See, if number of moles are same, then automatically number of molecules are same. So in Avogadro's law, it is a direct relationship of volume and number of moles, that they are directly proportional. Keeping what constant? Keeping pressure, keeping pressure and temperature constant. What are we keeping constant? Pressure and temperature both are kept constant over here. Clear, everyone? Now let's discuss about the ideal gas equation, everyone. Let's have a look on the ideal gas equation. See, if I am talking about what is an ideal gas equation and how you have to see basically how we derive an ideal gas equation. So we very well know that an ideal gas equation, it is basically PV is equals to nRT. This is ideal gas equation. What is an equation of state, everyone? What is the equation of state? Now, equation of state, basically we'll be establishing a relationship between two states, that is the first state, the initial state and the final state. So what are you going to get? You will get P1 V1 by T1 is equivalent to P2 V2 by T2. This is basically your equation of state. What it is? P1 V1 by T1 is equivalent to P2 V2 by T2. And let me tell you, so many questions from this are being asked. Now, how we have derived this? We have derived this by equating all the four laws. That is, the very first law that I am talking about is Boyle's law, then the Charles law, then the Avogadro's law, Gay-Lussac's law. So we are going to use all of these laws over here, and we established an equation of state, that is P1 V1 by T1 is equivalent to P2 V2 by T2. Keeping temperature in Kelvin over here. Do remember this key concept over here. Clear, everyone? Now I'm going to, students, start with your next topic, that is your Graham's law of diffusion. I'm going to start with Graham's law of diffusion. So if I'm talking about Graham's law of diffusion, understand, students, first of all, what is a diffusion? Diffusion is basically movement of particles from one position to the another position. Very simple. So then what is an effusion? Let's talk about them in detail. Very simple key concept. See what happens. For example, if this is a beaker and we have kept some particles here and some particles here. So movement of particles from one chamber to the another chamber is basically a diffusion, right? Movement of some particles from here to here. Okay, that is basically a diffusion. But if I'll say that if you have to do a movement from a particular small area, small hole, so that is effusion. Movement of a particles from a very small hole, that is effusion. Okay, for example, perfume sprays that you have with you. What is a diffusion? Movement of particles from one region to the another. Now, in depth, if you want to understand it, we have done osmosis, we have done what is diffusion. So with that, to solvent and solute, that comes under in depth, but yes, here we should know what is a diffusion and what is effusion. That is what is required. Yes, now understanding what is Graham's law of diffusion, they always says that it is valid for non-reacting gases. For example, if we'll keep two non-reacting gases all together, how are you going to calculate their pressure over there? So if you are keeping two, for example, non-reacting gases A and B all together, you should know the pressure of A is equivalent to the mole fraction of A into the total pressure. Similarly, if you have to calculate the pressure of B, it will be equivalent to the mole fraction of B into the total pressure. This is also a derived state. Now, students, as you all know, it is the ultimate recap session. So, I'm just writing the formulas so that you can revise with your notebooks, okay, the derivation part. Now, what is mole fraction of A? Mole fraction of A is basically number of moles of A divided by total moles, that is moles of A plus moles of B. What is mole fraction of B or zeta B? That is number of moles of B divided by total moles, that is moles of A plus moles of B. And even if you have calculated one mole fraction, you can calculate other how. Mole fraction of A plus mole fraction of B is equivalent to 1 by this formula. So basically, Graham's law of diffusion tells us about the pressure that is exerted on the walls of container. So by this way, we can easily calculate that pressure. Is it clear to each and every one of you? Please kindly write it down, students, so that I can now move on to the next part of mine. You can even write this is used for two non-reacting gases, everyone. You can write it down. This is used for the non-reacting gases. The non-reacting gases. Yes, everyone. More things what Graham's law of diffusion stated us. that students, the rate of diffusion, is directly proportional to pressure, and is inversely proportional to what? The root of molecular mass. And is inversely proportional to what? The root of molecular mass. Clear? Clear, 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 clear. Okay, that's really great. Now, it even stated that rate of diffusion in terms of volume, you can say that is referred to as volume escaped per unit time. Volume escaped per unit time is also the rate of diffusion. Even the rate of diffusion can be determined as rate of diffusion is number of moles escaped from one part by time taken. Even if you have to define rate of diffusion with regard to the distance traveled, so you can say that rate of diffusion is equivalent to what? It is basically distance traveled. It is basically the distance traveled by the time taken. So they can give you two various formulas. For example, if they'll give you two molecular mass and they will ask you rate, so you should know how you get to write rate. 1 is equivalent to square root of m2 by m1. How? Because rate is inversely proportional to the square root of what? First molecular mass. Rate 2 is inversely proportional to the square root of m2. In such a way you have to do this. Okay, clear everyone? Is it clear to each and every one of you? Please everybody write it down so that we can now move on to the types of speed. Everyone, write it down. Okay. Now let's talk about the types of velocity. The very first is basically the root mean square velocity. Okay. The root mean square velocity basically is your root 3 RT by M. Root 3 RT by M. This RMS basically refers to root mean square velocity. Everybody please write it down. This is root mean square velocity. This is root mean square velocity. If I'll talk about the average velocity, it is root 8 RT by pi m. It is root 8 RT by pi m. Root 8 RT by pi m. Everybody just write it down. Everybody just write it down. And yes, students, these velocities are, we have got these velocities from a particular graph where we determine that how many fraction, when we are drawing a graph of fraction of molecules and the speed of the molecules, we observed that the three types of velocities are obtained. Okay. Everybody just write it down. Create a formula sheet for the students. I guess everybody has written this. Yes, there is one question that is asked, that is what is the ratio between all of the three's velocity, that is most probable speed, root mean square velocity and the average one. So yes, one question is asked about ratio of most probable speed, and then we have root mean square velocity, and then we have the average one. So such questions are generally asked in exam. So you very well know the most probable speed is root 2 RT by m. Okay. Sorry, I have not written. You can write it. Most probable is root 2 RT by m, right? So you can write it as 2 RT by m ratio. What is root mean square velocity? It is root 3 RT by m. And what is average one? It is 8 RT by pi m. See, over here we can say RT by m is constant. So we can say root 2 is ratio root 3 ratio root 8 by pi. Now see, they can confuse you in such a way. They'll ask you the ratio of RMS then average then MP, or they can ask you the RMS MP then average. So you should know all the three formulas, then only you can answer this part. Right, students? So such kinds of previous year questions are being asked in this case as well. Yes, everyone, it's clear. I hope so it's clear to each and every one of you. Okay, let's talk about the compressibility factor now before moving on to the, okay, let's start with the kinetic theory of gases and then we'll move on to the next part. So what exactly is kinetic theory of gases and what are the postulates of kinetic theory of gases? Let's understand about them. See, there are certain postulates of KTG, that is kinetic theory of gases. Basically, we have to consider it in a hypothetical way. How? See, the gaseous molecules are considered to be point masses, okay? They're considered to be a point masses. Next part, you'll get why we are saying that. The volume of a molecule is negligible as compared to the total volume of the gas, okay? So that means if volume of the molecules are considered negligible to the total volume, that means their volume will be compared equally to that volume of the gas, right? So because they are considered negligible. The molecules neither attract nor repel each other. Very interesting part. According to kinetic theory of gases, the molecules neither attract nor repel each other. The collisions are perfectly elastic. Okay, now the collisions, that means when they bombard with each other, they are perfectly elastic. What is elastic? That there is no loss of energy during the collisions, right? Now, the average kinetic energy, see what is exactly, I would say, the main postulate of KTG. So, the main postulate is this one. What is the main postulate, ma'am? The average kinetic energy of the molecules is directly proportional to the absolute temperature. Very, very important. Average kinetic energy is directly proportional to the temperature, everyone. Very, very important as per the KTG, right? The effect of gravity in the molecular motion is negligible. Now, when we'll be talking about, the real gases, because ideal gases is something which is hypothetical, which we considered according to KTG. There is no force of attraction, no force of repulsion, volume is considered negligible. But in reality, students, if I'm talking about a particular molecule or a gaseous molecule, they have force of repulsion. They have force of repulsion. We have seen in gases now. So that's why real gases and ideal gas behavior are totally different key concept. Yes. What are they exactly, ma'am? If I'll talk about the ideal gas behavior and if I'll talk about the real gas behavior, students, the ideal gas basically states the follows completely the KTG theory of gases. But real gas states that no, it is hypothetical. It is hypothetical. It is assumed one. We have considered it is going to be like this. Volume is going to be like this. There is no force of repulsion attraction. No. But in actual, in reality, there is a force of attraction, there is a force of repulsion. So that means in ideal gas, if we are saying PV is equivalent to nRT, but in actual real gases, PV is not equal to nRT. It is not equal to nRT. It is a hypothetical situation. It is a hypothetical situation that we have considered. See, now I am introducing to you a term that is Z, that is compressibility factor, which states that PV by nRT. This is the formula. Even it says that basically, it is basically the real gas divided by the ideal gas. This is the formula for the compressibility factor. Now see students, in the case of, if I'll talk about the ideal gas, for ideal gas Z is 1, but for real gas Z is not 1. Why? Z is PV by nRT and here PV is equals to nRT. So here Z will come out to be 1, but over here Z is not 1. Z can either be greater than 1 or Z can either be less than 1. Yeah, there are two different situations that we are going to understand. Now, ma'am, what is the real gas equation? See, remember, what is an ideal gas equation? What is an ideal gas equation? The ideal gas equation, ma'am, is PV is equals to nRT. But what is the real gas equation, ma'am? Real gas equation is not that. Real gas equation is not at all that. Okay, P plus A N square by V square. V minus NB is equivalent to nRT. This is basically your real gas equation. Everybody just write it down. This is your real gas equation. Now, what is this, ma'am? What is this? Instead of pressure, ma'am, we are writing this complete term. Instead of volume, we are writing this complete term. Yes. So, basically, what we observe in real gas, there is a pressure correction term, there is a volume correction term. Let's understand it. See what happens in real gas. They say in reality, there is some force of repulsion, forces exist between molecules. Due to that, when there is a force between the molecules, so there will be a pressure correction term. There will be a pressure correction term, right? And due to, when we are talking about volume, yes, they exhibit some volume. So they were saying that the volume of molecules is negligible. No, they have some volume. If they have some volume, so they have a volume correction term. Volume correction term. Now, in pressure correction term, let's understand if I'm talking about, according to KTG, what was happening. If we have some molecules, basically they were saying that They don't have any kind of forces of attraction, neither repulsion. If they don't have it, they will only strike to the walls of the container. They will only collide with the walls of container. But I am saying in reality, they have forces of repulsion and a very few force of attraction. They are colliding with each other. So that means the pressure is going to be changed. How much it is going to be changed? It is also a thing that we need to think upon, right? So basically here the pressure correction term is introduced because why? Because the molecules exert some pressure on the walls of the container as well as with each and every molecule on each other. For example, on the walls and as well as with each other. So pressure correction term, that is changed volume. The new volume comes out to be what? New volume for a real gas comes out to be P plus AN square by V square. What is A? A basically is a van der Waals constant, right? Similarly, B basically is a constant over here. Now, what is volume correction? See, we were saying that the volume of molecules is negligible. That means the total volume is equivalent to the volume of gas. So if I have to calculate, if I am saying that yes, it do have some volume, it is not a point mass, it is a huge sphere, it has a mass on it, it has some volume in it. So that means the volume that we were considering, if we'll subtract the volume of the molecules, we are going to get the exact volume. If we'll subtract the extra volume, we are going to calculate the actual volume. So now here we subtract some volume, that is V minus NB. So what are we getting? We are getting the volume correction term. So when we introduce both of the things over here, we are getting a real gas equation. Everybody just write it down. Everybody just write it down. It is very simple key concept, nothing. It is very simple key concept. Now starting at when we say at high pressure. At high pressure, what will happen? At higher pressure, P plus AN square by V square will be negligible now. This thing will become negligible now. It will become negligible now because this is very small amount. No? This will become negligible. So at high pressure, what will be our new equation? It will be basically P plus AN square by V square. V minus NB is equivalent to nRT, no? So here if it is negligible, can I write it as P? P plus V minus NB is equivalent to nRT. Can I open it? It will become, sorry, here is not a plus sign, here is a multiplication sign. So what are we going to get? PV minus PNB is equivalent to nRT. Let's consider for 1 mole of a gas. For 1 mole of a gas, N value will become 1. What we will get? PV minus PB is equals to RT. Now students, what you have to do is divide each and every term by RT. Divide by what? Divide by RT. What are you going to get over here? Just see. You will get PV by RT minus PB by RT is equivalent to RT by RT. See, RT by RT is 1. And what is PV by RT? See, we know that Z is PV by nRT. For 1 mole of a gas, N is 1, so Z is PV by RT. That means this is Z. What we'll get? Z minus PB by RT is equal to 1. Simple, no? Yes, everyone. So what is Z? Z comes out to be 1 plus PB by RT. That means Z value is more than 1. In which case? At higher pressure. So Z value is more than 1 at which case? At higher pressure. Clear, everyone? Yeah. Clear, everyone? Okay. Now, if I am saying at low pressure, what happens? If pressure is low, volume is high. But obvious, if pressure is low, volume is high, P according to PV is equals to nRT because they're inversely proportional to, or you can say at higher volume. So, at low pressure, volume is high. If volume is high, we can neglect V minus NB. It is approximately equivalent to V. What is a new equation? P plus AN square by V square. V minus NB is equivalent to nRT. Right? So here this is same P plus AN square by V square. This we will say as V is equivalent to nRT. Now N basically is going to be 1. Let us consider for 1 mole of a gas. So we'll get P plus A by V square into V is equivalent to RT. Let's multiply them all together. What we will get? PV plus AV by V square is equivalent to RT. Now this VV gets cancelled. We'll get PV plus A by V is equivalent to RT. Divide by RT on both sides. So you will get PV by RT plus AV RT is equivalent to RT by RT. This is again 1. This is Z. Z is 1 minus AV RT. That means Z is less than 1. For which case, at low pressure when the volume becomes high. At low pressure when the volume becomes high. Clear, everyone? Yes. So students, it was all about this particular chapter. See, we do have some kind of types of attractions, that is dipole dipole interaction, dipole induced dipole interaction, but yes, that we have studied in detail in the previous chapters, so I've not discussed that over here. But yes, I have completed each and every topic over here. As I've already told you, this is a quick recap session, so we are just revising all the formulas, all the parts that we have studied in this chapter. So yes students, again repeating, if you have to study it in depth, you have to revise the complete chapter, open up your NCERT, solve the questions. This is a short recap session where you can prepare your short notes for your exam and do well in that, right students? Now we shall be meeting in the next class. Till then, keep smiling, keep learning. Thank you so much and have a good day, my dear students. Thank you.